So now let's discuss the case second of the theorem. Case second, okay. So in case first we have assumed that measure of E is finite. So now we have case second. In this case, we take if the measure case second if measure of E is infinite. Measure of E is infinity. So in this case, we define for each fixed I, we define for each fixed I, define Bi, which we call the ball, with the center at 0, Bi, which is equal to the set X belongs to Rn, set of all n tuples. So it's a ball in Rn, n-dimensional ball, such that distance between X and 0 is less than I, less or equal to, it's a closed ball, okay, with center at 0. Let's define this ball and define the sets and define this and we define these sets EI, which is equal to E intersection BI. Since E is measurable, BI is measurable because it's actually closed subset for it, every closed subset of Rn is measurable. So this means that then the E is measurable, and then E is measurable, and this measure of EI, so it's EI actually, not E is then EI is measurable. As E is measurable, BI is measurable, and measure of E is less or equal to measure of this bounded ball with center at this 0 and radius I. So this measure of this ball is finite. Okay. So EI is a measurable set and its measure is finite. So its measure is finite. Okay. So I have to introduce actually, it's a Lebesgue measure, not the general measure. It's Lebesgue measure here. It's Lebesgue measure, okay? It's Lebesgue measure here. It's Lebesgue measure, okay. So this Lebesgue measure of the set, because Lebesgue measure is a monotone, so it's less or equal to this as EI subscript BI, because EI is the intersection of E with BI. So therefore, by case one, we can find for each I there exists an open set. Therefore, by case one, for each I, there exists an open set OI such that this Lebesgue measure of O, such that EI is subset of OI. EI is subset of OI. So this exists for this EI actually, I measure finite, and Lebesgue measure of OI minus EI is less than 2 power minus I into epsilon, 2 power minus I. This is our epsilon actually, okay? For each epsilon positive, I can find some open set OI such that EI is subset of OI and Lebesgue measure of OI minus EI is less than 2 power minus I times epsilon. Put O is equal to union OI. I runs from 1 to infinity. I is a positive integer. I runs from 1 to infinity. Then clearly O is an open set. Then clearly, because it's a union of open sets, then clearly O is an open set. O is an open set. Also we have this, also this E, its union of EIs, you can easily verify it. Its union of EI runs from 1 to infinity, because union of BI is actually whole Rn. You can easily verify that union of BI is whole Rn, therefore E must be equal to union of EIs. You can easily verify this. I will leave this as an exercise to verify this. Okay, to verify this E is union of EIs, using the fact that union of BIs I runs from 1 to infinity is equal to Rn. So this is union of EIs, and O is the union of open sets. Then O is an open set. Then this E, it is subset of, is union of EIs, and each EI is subset of OI. So union EI must be subset of union OI. So it's a subset of union. Sorry, it's a union OI. It's a union OI. Okay, it's union OI. Subset of union I runs from 1 to infinity. It's also I runs from 1 to infinity. This union is equal to O. So E subset of O. Now we try to find this Lebesgue measure of O minus E, and you can verify this. This Lebesgue measure, it's less than epsilon. So I will leave this as an exercise. It's less than epsilon. Verify it. Okay, verify it. So this proves the one of this theorem. Now we prove converse. Okay. So conversely assume that for each epsilon positive, there exists an open set O such that E subset of O and Lebesgue measure of O minus E is less than epsilon. Suppose this is true. We show that E is measurable. We show that E is measurable. We show that E is measurable. Okay. So for each I, choose an open set OI. For each I, for each positive integer I, choose an open set. Choose an open set OI. For each positive integer I, choose an open set OI such that this E is subset of OI. E is subset of OI, and the Lebesgue measure of OI minus E is less than I power minus 1, and Lebesgue measure of OI minus E is less than 1 divided by I. Okay, it's 1 over I. So this is true because for each epsilon positive I can find open set O such that Lebesgue measure of O minus E is less than epsilon. Now now for each positive integer I, so I can treat this is a positive integer, 1 over I is also a positive integer, so I can treat epsilon equal to 1 over I. So for this epsilon equal to 1 over I, we can find an open set. So let's denote that open set by OI, because these open sets, they actually depend on epsilon. For each epsilon positive I can find open set O. This open set would definitely clearly depends on epsilon. So here this open set OI, it depends on the positive integer I. That's why we have denoted it by OI, such that E subset of OI and Lebesgue measure of OI minus E is less than epsilon, where epsilon is here 1 over I. Okay, this now we define the set. Define put G is equal to intersection OI. I runs from 1 to infinity. Then this E, which is subset of each OI, therefore E is subset of the intersection OI, I runs from 1 to infinity, which is equal to g. And let's find this Lebesgue measure of g minus e. What what will be this Lebesgue measure of g minus e? It's obviously because this g is subset of oi. G is subset of, as g is the intersection of oi, therefore g is subset of each oi. Okay, g is subset of each oi. Therefore, this is less or equal to Lebesgue measure of oi minus e. But Lebesgue measure of oi minus e is less or equal to, it's less or equal to 1 over I. This is true for all I greater or equal to 1. Letting I approaching to infinity, we get Lebesgue measure of g minus e is 0. So which implies g minus e is a null set, which implies g minus e is a null set. Okay, g minus e is a null set. It's a null set. So that means that g minus e is measurable, because every null set is measurable. G minus e is measurable. Now what's e actually? We have to show that e is measurable. Now e, which is equal to g minus e, it's equal to g minus e. It's equal to g minus e. You can see it here. It's g minus e. Okay. Okay. It's g because this e is actually subset of g. So this is a set. You can. This is your set e, and this is the set g. Okay. E is subset of g. And now what you are doing, g minus g minus, you are first find this g minus e, which is equal to this set. This set is g minus e. Then what you are doing, you are taking out this portion g minus e from g. It's g is this whole, g minus e. That's obviously this set. Okay, this set is this set. Let me this set is actually, this set is e, and it is same as g minus e. Okay, so this e is equal to g minus e. Since g minus e is measurable, g is measurable, and difference of two measurable sets is measurable, which implies e is measurable. E is measurable. So that proves this theorem completely. Now we have more theorem. Every Borel subset of Rn is Lebesgue measurable. Every Borel subset of Rn is Lebesgue measurable. Okay. Proof. Every Borel subset of Rn is measurable. So let you know what are Borel subsets actually. Yeah? The sigma algebra generated by the open subsets of Rn. That sigma algebra, the members of those that sigma algebra are called Borel sets. So let minus infinity less than ai less than bi and less than infinity. Okay. For I runs from 1 to n, because you had because you are in n dimensional space, I runs from 1 to so on up to n. Choose m such that since this bi is ai is less than bi, we choose m so large. Choose m such that this ai plus 1 over m, this m is so large such that ai plus is less than bi, is less than bi for all I, for I equal to 1 to up to n. Okay. Then one can easily verify that then this product of n copies of open intervals, it's the open interval of Rn, which is equal to the union I runs from I runs from m to infinity. I runs from, sorry, I will write here k because I is already there. So I will write here k runs from 1 to infinity, k runs from m to infinity, and then I will take the product I runs from 1 to n. This theorem we have already done for real line. Now we have to do this theorem for n dimensional space Rn. Okay, this is already done for the you can see the proof for real line there, and then you can easily understand this result. K runs from m to infinity, I runs from 1 to n is here. Okay, it's here 1 to m. I runs from 1 to m. Okay, yeah. Now this one, you can see these. This is actually the member of the semi-ring, because it is the product of n copies of semi-closed interval. Therefore, it is in the semi-ring. Since this product of the k copies, I runs from 1 to n, ai bi, it belongs to the semi-ring S. So that means this is measurable, which implies this set is measurable. Sorry, it's ai plus 1 over m actually. It's ai plus 1 over m. It's ai plus 1 over m. This is ai plus 1 over m. Yeah. So this ai plus 1 over m comma bi, because it is in the semi-ring and every member of the semi-ring is measurable. So therefore this is measurable. So from and we know that the countable union of measurable sets is measurable as the collection of measurable sets is sigma algebra. So therefore this is also measurable because it's the countable union of such sets which are measurable. So that means that implies this set's measurable. Product of n copies of open intervals is measurable. It's measurable. Is measurable. Okay, this is measurable, or I can say it belongs to lambda, because lambda denotes the collection of all measurable sets. Belongs to lambda. Okay, this set is measurable. Now I will show that every open set is measurable. Since as in case of real line, every open set can be written as the countable disjoint union of bounded open intervals, and same is true for Rn. Every open subset of Rn can be written as the countable disjoint union of these open intervals like these, they are bounded open intervals. Since every open set of Rn can be written as disjoint union of bounded open intervals. Bounded open intervals. So every open set can be written as this is called the bounded open interval of Rn. Okay, this set, it's called the bounded open interval of Rn, and every open set of Rn can be written as bounded disjoint union of bounded open intervals of Rn, and every such bounded open interval is measurable. Therefore, every open set is measurable. So this implies therefore every open set of Rn is measurable. So that implies that this is measurable, and this means this let O be an open set. O be an open set in Rm. So this implies O belongs to lambda. O belongs to lambda. But lambda that means this lambda is is a sigma algebra, is a sigma algebra containing each open set, containing each open set. So lambda is a sigma algebra containing each open set, but B, this fancy B, it is the smallest, is the smallest, is the is the smallest sigma algebra containing, but that's the definition, containing each open set. So therefore therefore every member of B, therefore therefore B is subset of lambda. Actually, B is a subset of lambda. Okay. Therefore B is subset of lambda. So that means this B, it contains each measurable set, which implies every open set is measurable. Every open set is Lebesgue measurable. Lebesgue measurable. Every open set, every Borel set is measurable. Not every open set, that's already done. Every Borel set is measurable, because B is subset. This B, the members of B are called Borel sets, and they are also the members of lambda, but the members of lambda are called measurable sets. Therefore, every Borel set is Lebesgue measurable. So this proves the theorem completely. So in the next theorem, we will try to prove Ostrovsky's theorem, which actually what are the measurable solutions of this function f of x plus y equal to fx plus fy. So this is if f is a measurable function, and satisfying this property f of x plus y equal to fx plus fy, then we show that this fx of this type, f of x equal to constant times x. But first we prove the theorem not for the measurable function, we prove the theorem for continuous function. If f is a continuous at 0, if f is continuous at 0 and satisfying this property f of x plus y equal to fx plus fy, then there exists c such that fx equal to c times x. Then we prove the same theorem for measurable function. If f is a measurable function satisfying this property, from this we show that f is actually a continuous at 0. From this equation, f is measurable and satisfying this equation, then we show that this f is actually continuous function. Then we use the result that every continuous function satisfying this property is of this type. So therefore every measurable function satisfying this equation, every measurable function satisfying this equation must be of this type. So this theorem is called Ostrovsky's theorem. Okay, Ostrovsky's theorem. So this we do in the next lecture. Thank you.